Have you ever actually stopped to wonder what it takes to build and manage the massive telecommunications networks we rely on every day?
And not just manage them, but seamlessly scale them.
Right, seamlessly scale them. Because we expect instantaneous connectivity, whether we're joining a high-definition video call from a moving train or deploying thousands of IoT sensors across a smart city.
Yeah, but beneath that expectation lies this incredibly complex, highly specific architecture.
Exactly. And that brings us directly to our mission for today's deep dive. We are jumping into a really specific, highly technical stack of source material,
Which is a study guide and practice test for the VMware 5V0-44.21 exam.
Yes. We're going to focus heavily on the actual exam questions and the answers provided in this material.
And just to be clear, our goal here isn't just to help you memorize a study guide so you can pass a test.
No, definitely not.
We are using these exam scenarios as a masterclass, really, to unpack the reality of modern telco cloud architecture.
It's an inside look at the blueprint. But let's set the stage first, based on the source material. If you were to sit down for this certification, you're looking at a pretty rigorous 105 minutes.
Yeah, it's not a walk in the park.
Not at all. You'll face 55 questions, a mix of single and multiple choice, all delivered in English. And to walk away certified, you need a scaled passing score of 300.
Right, and it assumes you already understand the fundamentals of virtualization and cloud environments. It tests very specific operational knowledge. You have to know how these tools interlock under immense pressure.
So let's get right into it. I've sort of categorized this first batch of exam questions as the brain and the blueprint.
I like that.
Let's look at the core orchestrator. The exam tests your understanding of component roles, specifically asking what component functions as the generic virtual network function manager, or GVNFM.
And the correct answer there is VMware Telco Cloud Automation, or TCA.
Right, TCA.
What's fascinating here is how TCA bridges the gap between traditional IT infrastructure and specific telecom requirements.
Because usually those are pretty separate, right?
Exactly. In the standard ETSI network architecture, you have this rigid separation of infrastructure management and network function management. But TCA collapses that complexity.
It doesn't just manage.
No, it automates the complete lifecycle. When a new 5G core component needs to be deployed, TCA handles the onboarding, the scaling, the healing, and the eventual termination. It serves as the definitive engine for service operations.
And to manage that life cycle, TCA needs to know exactly what it's building. Which actually brings us to the next exam scenario.
The modeling language?
Right. The test asks, which modeling language does VMware TCA use to define the overall structure and orchestration requirements of a network service?
And the required answer is TOSCA.
TOSCA, right. Topology and orchestration specification for cloud applications.
Yeah.
But my question when I was reading this was, why TOSCA? I mean, why not just use native Kubernetes manifests or standard Helm charts if we're talking about cloud environments?
Well, that is the exact distinction the exam wants you to make. Telecom networks are incredibly heterogeneous. You aren't just deploying a simple web app.
Right, it's not just a website.
You are deploying complex, multi-tiered network functions that might span across private data centers, edge locations, and public clouds. TOCA is an OASIS standard. It is entirely vendor agnostic.
Oh, so it doesn't care what the underlying hardware is.
Exactly. By using TOCA as the blueprint, TCA can parse a standardized declarative model that maps out the intricate relationships, the lifecycle hooks, and dependencies of a network service, regardless of whether the infrastructure is VMware, AWS, or bare metal.
Okay, let's unpack this. Because that word you just used, declarative, that is the focus of another major exam question.
Right, the orchestration models.
Yeah, the test explicitly asks about the advantage of using a declarative orchestration model over an imperative one. And the answer you need to select is, the system automatically works to maintain the defined desired state. But let me challenge that for a second. In a highly volatile telco environment, doesn't a strict declarative model make emergency troubleshooting a nightmare? I mean, what if an engineer needs to manually hotfix a failing node? If the system is constantly trying to enforce the original blueprint, won't it just overwrite their fix?
That is a highly realistic concern, and it gets to the heart of why modern telco cloud operates the way it does. Yes, if an engineer manually tweaks a configuration in a purely declarative system, the reconciliation loop will detect that the current state has drifted from the desired state.
And it overwrites it.
It will overwrite the manual fix to restore the baseline. But in cloud-native telecom, manual hotfixes are considered an anti-pattern.
Because they introduce configuration drift.
Precisely. The declarative model enforces immutable infrastructure. If there's a problem, you don't SSH into a server and patch it.
You update the TOSCA blueprint?
Or the Helm chart, and you push the new desired state through your CI/CD pipeline. The advantage the exam is highlighting is that TCA continuously runs these reconciliation loops. It completely removes the operational overhead of human engineers constantly monitoring and tweaking systems.
The platform itself guarantees the environment matches your validated, secure blueprint. It fundamentally forces better operational hygiene.
Exactly.
I like that. Let's shift from the orchestration layer down to the physical and virtual resources. We are moving into the building blocks segment.
The actual infrastructure.
Yeah. One of the core exam questions focuses on infrastructure management. It asks which platform is recognized as a supported virtual infrastructure manager, or VIM, that integrates with TCA.
And the answer to that is VMware Cloud Director.
Right. And from the source material, it seems VMware Cloud Director, or VCD, is critical here because of how it abstracts physical resources.
It is. While vCenter is great for managing ESXi hosts, telecom operators need a way to carve up massive data centers into secure, logically isolated pools of compute, memory, and networking.
So VCD acts as the VIM by providing these virtual data centers.
Right. It allows TCA to seamlessly request resources without needing to know the exact physical topography of the underlying blade servers.
And when we talk about those resources, we have to talk about where the data actually lives.
Storage.
Yep, the exam presents a scenario regarding storage integration. It asks, which software-defined storage solution is most commonly integrated with TCA to provide high-performance persistent storage for telco workloads?
And that would be VMware vSAN.
vSAN. And if we connect this to the bigger picture, vSAN entirely changes the economics and the architecture of telco edge deployments. Because traditionally, you would need dedicated, highly expensive SAN or NAS arrays.
Right, but at a 5G cell site or a far-edge data center, you just don't have the physical footprint or the power budget for massive storage arrays.
You are working with super limited rack space.
Exactly. vSAN operates natively at the hypervisor level. It aggregates the local solid-state drives from the individual ESXi hosts in a cluster and creates a single distributed object storage data store.
So let's say you have a localized hardware failure. A disk group dies during peak 5G traffic.
Because vSAN uses storage policy-based management to define redundancy per virtual machine, the data is already mirrored across other hosts. The telco workloads continue running without dropping a single user session, and vSAN automatically initiates a rebuild process in the background.
It builds resilience directly into the host layer. That's incredible.
It really is.
Now, as the industry shifts aggressively toward cloud-native network functions, or CNFs, the exam tests how we manage the actual code deployments.
The container images.
Right. The question asks, what serves as the central repository for storing and managing containerized images and Helm charts in a TCA deployment?
The answer provided is the Harbor Registry.
But Harbor isn't just about storage, right? It's heavily focused on security.
Absolutely, and that is why it is explicitly tested in this exam. Harbor provides project-level role-based access control and native vulnerability scanning.
Because in a telecom environment, you cannot just pull container images directly from the public internet.
No, that is a massive security risk. Harbor acts as your private, secure proxy cache. Before a containerized network function is ever deployed by TCA, Harbor can automatically scan it against databases like Claire or Trivy to ensure it doesn't contain known vulnerabilities.
Furthermore, it enforces image signing, guaranteeing the artifact is immutable and untampered with.
Exactly.
Here's where it gets really interesting. Because we're hitting the part of the exam that separates general enterprise cloud from dedicated telco cloud.
The hardware tuning.
Yes. General IT apps can handle a little bit of latency, but telecom workloads, processing millions of data packets per second, absolutely cannot.
No, they can't.
So the exam asks, which feature allows VMware TCA to optimize the placement of workloads based on specific hardware capabilities like CPU pinning?
And the answer is Enhanced Platform Awareness, or EPA.
We really need to dive into the technical weeds here. Why are features like CPU pinning and SRIOV so crucial for telecom?
This is the exact intersection where software meets physical silicon. Let's take CPU pinning first. In a standard virtualized environment, the hypervisor scheduler constantly moves virtual CPUs across different physical cores to balance the load.
For a web server, that's fine.
Right. But for a 5G user plane function routing gigabits of traffic, that context switching introduces unacceptable microsecond latency. CPU pinning reserves specific physical processor cores exclusively for that single workload, totally eliminating the scheduler overhead.
And the exam also mentions NUMA alignment and huge pages. I know NUMA alignment ensures that a virtual machine's compute processes and its memory allocation are kept on the exact same physical socket on the motherboard.
Right, because if a CPU has to cross the memory bus to fetch data from a different processor's memory bank, you get latency.
And huge pages is another memory optimization. By allocating memory in much larger blocks, say 1 gigabyte, instead of the standard 4 kilobytes, you drastically reduce the number of lookups the CPU has to perform in the translation look-aside buffer.
It's all about reducing the distance and the friction for the data.
What about SRIOV? That's single root I/O virtualization.
SRIOV is arguably the most critical EPA feature for data plane performance. Normally, network traffic hits the physical network interface card, the NIC, then travels through the hypervisor's virtual switch and then into the virtual machine.
But SRIOV bypasses the hypervisor entirely.
It does. It allows a single physical PCIe network card to present itself as multiple separate physical devices directly to the virtual machines or containers. The workload talks directly to the silicon, allowing for near bare metal packet processing speeds.
So EPA is the TCA feature that ensures workloads demanding these exact capabilities are strictly deployed onto the physical hosts that could actually provide them.
Exactly. It guarantees you aren't deploying a high-performance packet broker onto a generic low-spec server.
That is a brilliant breakdown. Let's move into our final segment, keeping the lights on.
Day 2 operations.
Yes, Day 2 operations, scaling, healing, and security. The exam tackles how the network adapts to pressure. It asks, what does the term scale-out specifically refer to during the lifecycle management of a network service?
And the correct answer is adding more instances of a component to handle increased load.
But since we are talking about telco architecture, how does TCA actually execute this compared to just basic auto-scaling?
The exam highlights scale-out because it relies on the stateless design of modern network functions. If you have a traffic spike, say a massive influx of devices registering on a network, TCA continuously monitors key performance indicators streamed from the infrastructure.
KPIs.
Right. When specific thresholds are breached, TCA automatically triggers a scale-out workflow. It provisions entirely new instances of the required components, attaches them to the necessary networks via Cloud Director, and updates the load balancers.
And because the components are stateless, meaning the actual user session data is stored in a separate shared database, these new instances can immediately start processing traffic without needing to synchronize existing state data.
Exactly. And when the demand drops, TCA triggers a scale-in event, terminating those extra instances to free up compute resources.
But what happens when things break? The exam asks, what is the primary operational goal of an automated self-healing policy applied to a network function?
The answer is to restore service availability by restarting or recreating failed units.
In a traditional IT environment, a server crashes, pager duty goes off, an engineer logs in, diagnoses the kernel panic, and maybe reboots the machine. Why doesn't that work here?
Because in telecom, human intervention is simply too slow. Service-level agreements dictate 5 nines of availability. You literally have milliseconds to restore service. TCA implements closed-loop automation.
Closed loop?
Right. If it detects that a virtual network function is no longer sending a heartbeat, the self-healing policy doesn't wait for human approval. Depending on the exact TOSCA definition, it might try to gracefully restart the service. If that fails, it will ruthlessly tear down the entire instance and seamlessly recreate a fresh one from the harbor registry on a healthy physical host. The singular goal is sheer availability.
It's ruthless efficiency. I love it. Finally, let's talk about who is actually using this infrastructure. The final exam question we are reviewing asks, how does the VMware TCA platform enable secure multi-tenancy within a shared telecommunications infrastructure?
And the correct answer is by implementing role-based access control and resource isolation.
How does this apply to something like 5G network slicing?
It is the foundational requirement for it.
Yeah.
A massive telecom operator isn't just serving consumer cell phones. They have enterprise customers, a hospital network, an autonomous vehicle fleet, a manufacturing plant, all running on the same physical infrastructure.
So multi-tenancy means these different tenants share the hardware, but their environments must be cryptographically and logically isolated.
Exactly.
So the role-based access control, or RBAC, handles the management plane.
Yes. RBAC ties directly into vCenter and VCD permissions. The administrator for the hospital network can log into the portal and only see, manage, and scale the specific network functions assigned to their organization. They have zero visibility into the autonomous vehicle fleet's configurations.
And the resource isolation handles the data plane.
Correct. Through Cloud Director's isolated organization virtual data centers, the actual compute processes, memory blocks, and network routing tables are kept strictly partitioned. Even if one tenant's environment is fully compromised, there is no lateral movement path to another tenant's environment on the same physical blade.
Thank you for joining us on this deep dive into the VMware Telco Cloud architecture. Keep exploring and we will catch you on the next deep dive.